like to welcome everyone to the webinar series of the Cybersecurity and Information Systems Information Analysis Center, CSIAC. Today's presentation is entitled Deep Learning for Radio Frequency Target Classification. My name is Steve Warzala, and I'm the CSIAC Outreach Manager. A few administrative notes before we begin. First, all phones have been muted except for the presenters. Questions may be asked at any time during the presentation by utilizing the chat function. Time permitting, your questions will be answered at the end of the session. The briefing slides and webinar recording will be posted on our website within a couple of days. And finally, I'd like to take a moment to acknowledge and thank our sponsor, the Defense Technical Information Center, DTIC. The funding that DTIC provides enables CSIAC to conduct these webinars. It's my pleasure to introduce our presenter for today's webinar, Dr. Tom Majumder. Tom is a senior electronics engineer with the U.S. Air Force Research Laboratory. His research interests include artificial intelligence and machine learning, synthetic aperture radar algorithm development for surveillance applications, radar waveforms design, and high-performance computing for SAR-based automatic target recognition. Dr. Majumder is also a senior member and distinguished lecturer of the IEEE. Last summer, Tom published a book entitled Deep Learning for Radar and Communications Automatic Target Recognition. I will now turn the presentation over to Dr. Majumder. Good morning, Tom. The floor is now yours.
Yeah. Okay. Good morning. Thank you, Steve, for organizing today's talk. And I'm really honored to talk about deep learning and radio frequency target classification to the research community. So without further ado, I think I'll go ahead. So yeah, next slide, please. Okay, yeah, so I'm going to the next slide. So again, as Steve mentioned, this talk will be on how we can apply deep learning based technique for radio frequency target classification. So I'll highlight like recent results and the technical challenges. One thing to mention to you, we have lots of slides to cover. So the reason I put is that there has been lots of work has been done recently by me and my team and Air Force Research Lab. So I just wanted to aware that we actually dig so much deep on this area of research, so that you should be able to reach to us if you have any specific questions. And so I'll talk some of the slides details, and some of them may not be talking so much detail because of the time. So however, you can reach me offline and I can discuss details in later. So I hope everybody will be fine with that. So yeah, next slide. So again, this work has been like we are working for so many years. So it's a collaboration with academia, industry, and also the government labs. So I thank all of the the research collaborator on these slides. So here is the outline of the talk. So like I'll describe or provide an overview of the problem and how we are doing it now. Then I will discuss what is ATR, or automatic target recognition, and then recent results for deep learning based ATR. And then I'll talk about advanced research. And then finally, I'll talk about the future ATR research. So, in these slides, you can see the radio frequency applications. So radio frequency applications span from surface or ground to all the way to the space. So if we talk about surface, Navy, they do, they have so much application on RF it. I don't need to describe it so much detail. Then Army, then Air Force, and of course to the Space Force. So it spans from, as I said, from surface to all the way to the space. So what are those applications? Again, like from target recognition, like what type of object, what type of vehicle, what type of car it is, to all the way to what type of signal it is, like what type of emitter or something like that, or like aircraft, ADS-B signal. So it goes on, list goes on and on. So in a nutshell, radio frequency applications will be a dominating kind of area that deep learning will be used a lot. So RF applications, like as I mentioned, like why we are so much to the for RF applications. So because it actually covers so much that that it works on adverse weather conditions like a snow, fog, night, sandstorm, etc. So that if we specifically talk about surveillance or target recognition, so people used a lot for video imagery classification. So as you can see, the video imagery are not meant to be working on adverse weather. So that's the main area or main thirst of research, that why radio frequency is so much important and we need to work a lot. Then long range remote sensing for ISR, again, we use the radio frequency for that. Then self-driving vehicles. So besides the DoD applications like self-driving car technology, they also need RF. Then security and surveillance and multi-sensors object classification and medical diagnostic. So for COVID-19, like infection detection from chest X-ray, it's also an RF application, radio frequency application. So believe me, there has been some cases of COVID-19 that I know from the physicians that sometimes it is hard that whether a person has COVID or not. So therefore they use the chest X-ray with other information, whether it is COVID-19 or not. So here is video imagery versus radio frequency signature. So you can see in the top imagery shows the military vehicle. If you can see from video or electro-optical imagery, and the bottom you can see the SAR images of the same object. So as you can see, it is not visible from a naked eyes that the SAR images what type of target it is. But as I will show, that deep learning is really good to detect the object and classify the object from SAR images, as even though for us it will be hard to compare from the imagery to the top to the imagery to the bottom. So again, the top imagery are video or electro-optical imagery, and the bottom images are the SAR. So again, we have been done extensive research since 2014, and I think SAR image classification is in deep learning is become a prominent way of classifying object. So here is how polarimetric SAR imagery. So now some of the imagery you have seen or radar imagery you usually see black and white. So because we use mostly single polarization imagery like HH or VV. However, you can make 3D imagery or polarimetric images using HH, VV or cross pol. So what does it gives us? It gives you more information or more accurate information. You may use 3 channels in a deep learning methods so that your information will be more accurate. So this picture shows that how you can get more information if you use multiple polarization, and we can use those multiple polarization imagery for deep learning based target classification. So here is the slide. It shows object signature across various spectrum. So as you can see, top left, Ka band SAR HH then K-band SAR VV. So just compare these two. Actually, you can see if we use two different polarization, you may get different information, and if you combine them, therefore you get a better or more accurate information. So but in general, like we try to show that how in a different spectrum how a target look like for target classification. So what it shows that we may have to utilize multiple spectrum or multiple polarization to get even high accuracy for target classification. So the radio frequency data. So now one of the things needed for deep learning based target classification is data. So as you can see, if you can take your iPhone or video camera outside and you can really collect so much data you needed for target recognition or machine learning based applications. So however, radio frequency data are difficult to collect. So therefore, that's really one of the challenging area that we don't have lots of data. So also the measure data collection involves like RF sensors, integration and data collection by certified aircraft, and detailed experiment design and ground truthing. So that's the reasons like obtaining measured radio frequency data are very expensive. So like synthetic RF data or measured RF data for synthetic aperture radar, you can collect like 1D SAR, which is like the range profile. So again, SAR is synthetic aperture radar, so we can collect like a one-dimensional SAR, which is range profile. Then we can collect two-dimensional SAR, which is like image. And so in general, like most of the radar data are collected X band with 0.5 gigahertz bandwidth to provide 1 foot resolution. So now that's like for measured data. So how we can do with the synthetic RF data? So it is possible to generate radar data by simulation. So we can use the electromagnetic prediction code and using high performance computer to generate the synthetic data. So however, like when we do use HPC, it also requires like days to generate like synthetic RF data of a vehicle or object. So, and also compute time depends on high fidelity or the accuracy, number of objects in the scene, and background clutter of the scene. So nevertheless, like if we use a high performance computer, we can generate synthetic data for radio frequency research. And that actually gives us lots of latitude in terms of like, getting so much of data that we needed for machine learning research. So we cannot ignore the importance of synthetic RF data. And I'll talk about this more later. So here in this slide, I just wanted to give radio frequency data source available for AI or ML, artificial intelligence and machine learning research. So the reason I put these slides together because many people are not aware of these data sources, and I know many organizations, they are kind of trying to find out how we can get so much of data. So here is a list of public release or publicly available data set could be used for radio frequency research. So the first one is MSTAR public release data. Perhaps like if you see deep learning based SAR object classification, maybe 95% of the research are based on MSTAR public release data. Then another one has been published, is called SAMPLE Dataset. I'll talk more later. So this is like the AFR published called SAMPLE Dataset, which is actually they provided two dataset, one for measured RF data, and another one is synthetic RF data. So they try to say that, okay, if you try to train a deep neural network on synthetic data and test on measured data, how the results will be good. So we'll talk more about that later. So the sample data set provides you train a deep neural network on synthetic data and test on the measured data. And so this is like another public release data set that could be used for machine learning research. Then AFRL Sensors Directorate also published another data set called PEMS Dataset. Again, this is also available website. Then civilian vehicle dataset. So the civilian vehicle dataset is meant to be providing how we can classify a civilian vehicle. So this dataset is also available, and I provided the link. And then there is another dataset called ship detection dataset. So that was actually really unusual. So the Chinese government, for some reason, they actually published this dataset, and it's available GitHub. And truly, they actually provided this dataset comes from some of them from their satellite collection dataset as well. So they provided some challenge problems. So usually, we try to give challenge problems in RF target classification, but for some reason they are now overreaching, and they provided this dataset how we can detect and classify ships with high accuracy. So again, you may find out this dataset very interesting. Then in another application in RF domain is RF signals classification. So the Northeastern University, they actually public released or they provided a dataset for radio frequency fingerprinting of different Wi-Fi and other type of devices. So these are the handful of datasets. So I hope this list will help each and everyone here to know that, okay, well, if I would like to do radio frequency research, where should I start? So again, you cannot just develop the algorithms. As much data you need, your algorithm could be more robust, and also more about how to bring deep learning for radio frequency applications. So this data set is actually will be very useful, those who would like to start your research. So again, I'm going back to MSTAR. So MSTAR, those who doesn't know, MSTAR is Moving and Stationary Target Acquisition Recognition program. It was back in 90s. DARPA and AFRL Census Director, they started working together. So these are the data set that 10 classes of data sets the public release available, and these are collected on 17 and 15 degrees, and these are the number of images for each class. The sample data set, as I mentioned, a synthetic and measured paired leveled experiment data set. So again, these are also X-band radar and available for research. So I'm not talking a lot to save my time, but these are self-explainable here, and you can find the associated papers they published at SPIE to know detail. And then the PEMS dataset is a performance estimation for multi-sensor ATR data. So again, this dataset, I think in the slide is self-explanatory, and also the paper and the publication is in this slide, so you can read more. But then you may ask how it is different from sample dataset and PEMS. The PEMS actually cover more articulations and more what you can say that more angles and more variety for operating conditions, different operating conditions. So this a data set is more add you more complexity than the sample dataset. The civilian vehicle dataset, again, X-band data, and then these are the vehicles a Toyota Camry, then Civic, and again a commonly available civilian vehicle dataset. Then the RF ship detection dataset, as I mentioned, the Chinese government published this dataset, and so this is also available. But one thing to mention here, some researchers, they're saying that whether this dataset is actually real, or they try to fool us, to say that, okay, well, we may make our deep neural network based on these are the ships and these are some characteristic, but they may be trying to see how we react, and whether we just develop a deep neural network model on this dataset and then deploy them, and then we may have some adversarial impact. We may not really classify the real target as what it should be. So there is a bit of caution of this dataset, whether they have done any adversarial perturbation on the data set. So you have to be careful. But nevertheless, I think you can use this data set and see what it is. So now, I'm just giving you some basic things. I know many of you here could be the advanced researcher or manager, but those who would like to get into. So we hear AI, which is artificial intelligence, machine learning, ML, and DL. So what are those are? But I think we need to know who are the pioneer in this area. So Professor Jeffrey Hinton from University of Toronto, the Ian LeCun and Yoshio Bengio, they are considered the godfathers of AI and deep learning. And so now some of the distinction of AI is machines things to behave or react, and what is a ML is a data-driven process for machine learning to learn, and deep learning is a brain-inspired neural network for robust methods. So again, these are the same topics comes over and over, but one distinction is say you can think of AI is the everything. If we have an automated if you have an UAV that actually controls itself, so it's like an AI or expert systems. It's an AI. It's autonomous. Then machine learning is a subset of AI, and the deep learning is a subset of machine learning. So that's how to think how those three things kind of goes together. So in the top right corner, you can see the artificial intelligence the kind of superset. Then machine learning is a subset of artificial intelligence, and then deep learning is a subset of the machine learning. And next. So the machine learning algorithm. So again, I think at this point, many of the researchers, they are very clear that what is machine learning all about. But I try to put together as a broad categories. So the machine learning, when you think of, it's a supervised learning, unsupervised learning, semi-supervised learning, transfer learning, reinforcement learning, and generative adversarial network or learning. So again, you can categorize more within supervised, which we mostly use, deep neural network. So we have linear classifier, non-linear classifier. So the linear classifier, you can have perceptron, support vector machine, passive aggressive, and linear regression. So then non-linear or unsupervised learning, you have K-mean clustering and Gaussian mixture models. So and on and on. So I think these are self-explanatory. So hopefully, again, to save time, I'm not explaining all of those details. Hopefully, you can learn from the slides. So now the webs of AI. So according to DARPA, we kind of, they classify the artificial intelligence as three webs. The first web is handcrafted knowledge. Again, the machine is not learning, but we are just programming the machine to do some from recognition. The second web is more of systems that learn statistical models of specific problems using big data. So the deep neural network that we are using now, these are second web. The third web is contextual adaptations. So that's a more of a reinforcement learning that, it's a collaboration of human and machine interaction, and then a machine should makes update or, learn by itself. So we are heading into the more of third web, getting into third web of AI now. So a top 5 deep neural network architectures. So LeNet and AlexNet, VGG, and GoogleNet and ResNet. Those are the couple of the top deep neural network architecture. And I think you can get those things from this lecture from Stanford. And some of the software tools used for deep neural network is Python or PyTorch. Then also you can use an Amazon Web Service, and they have all the GPUs, and Google Colab, and then of course the NVIDIA GPUs. So those are the tools we needed for deep neural network based target recognition application development. So so here is a kind of a very brief overview of deep neural network, how it looks like. So we have a car, and then we try to we have a training data. So we try to see that how close the data set looks like to be a car, and only give an estimate that it's a 90% accurate that this is a car, or this is a truck, or this is a tank. So it's a back and forth process of learning. and with the trained data that we make sure that it's a car is a car. And so the behind the scene is like a really optimization and error optimization process and calculating the weight. So those weights are like the crucial parameters at the end to work with an object and say that it is car or truck or tank. So it's again a convolutional neural network. So it's like one of the common method. Like we use convolution like a 3x3 filters, and we just do those the kernel pass over to the entire image and try to find some object of interest or not. So I'll not talk these are very details because we go to the RF applications pretty quick. So now at the end, like if you would like to know all about today's talk, so like as Steve mentioned, so we have a book on deep learning for radar and communications ATR. So so far what we have talked, you'll see all of those things, in our book published by Artec House. So it actually has all the details. And one thing, like the research community, in particular RF and ATR, they look for this book for so long. So we try to give a really deep understanding of what is involved with RF target classification. So like I hope that today's talk will be actually give a glance of what's there. But of course, like you can get all from this book, all the details in the book. So now the ATR. So what is the automated target recognition? So automated target recognition is the computer process, getting image, sensors, or other sources from a single or multiple mode and making a decision that what it is or what's the intent. So within ATR, automated target recognition, actually it involves a lot. So first it will sense and get the signal imagery from RF, EU, and other sources and think, and then act, what to do, sort of things. So that, and ATR actually, someone said that, okay, ATR is actually finding a final product as an ATR. It's a tough process because it has to go through so many steps. But like, many cases, like we do half type of ATR, in a sense that, okay, is there a target presence in the scene or not? We may just say, okay, this is an ATR. Yeah, that is a man-made object like a car or building. We just say that, okay, yeah, it is an ATR. So however, like if you go through the nomenclature, as you can see here, detect, classify, recognize, identify, and screen and behavior. So all of those are part of the ATR. So ATR itself is really a huge area that, to make sure that, everything works properly. So the reference to that, in the paper here, you can find more details on that. So then SAR ATR approaches. So like in the past, ATR was more of template-based approach, and still there are so much algorithms are on template-based approach. So in template-based approach, what it does, you take a signature of the target and then basically correlate with a new image and see that whether it is a target or not. But as you can see, it's like a more of a first wave of AI. There is no learning things. It's like a more of a memorization. So meaning that if there is a slight change, your results will be really bad. So then they try to develop model-based approach. So like more of 3D structure and do it. But it helps a little better than the template, but again, it's not doing much. So then like here is as I said, template-based approach. What it does, it's a correlate an unknown image with a known image and see how it's good the match it is. But this process costs like a lot, like a data processing, storage, and collections, because you need millions of templates, to really classify this target in a good accuracy. So again, more details on this could be found on the paper here. So now here is like an example. I'm showing you why template-based approaches are bad. So in a way that you can see that like here BMP2-3, so it was trained with this target, like a version of BMP2, but when you test with the BMP-2, your accuracy really degrades. It's not, because it's not exact matching. And then most importantly, like if you see T72 tank, if you train with the version 1, it gets 95%. However, if you have a similar version, different version, like say you take out the barrel or other part, like T72 to 72-2 or 3, performance like really degrade significantly. So therefore, template-based was not the approach. So that's how like some of the program came, like a DARPA trace program came back in 2014. They tried to do it. And so they applied the same technique on the MSTAR dataset, and they found 99% accuracy. But again, this is like a more of a toy problem to start the program, like a trace program start. And then subsequently, they have developed like a more the trace program with a $50 million investment. They actually developed more advanced deep neural network based target classification, and they provided really good accuracy. So now, again, as I mentioned, like ATR is really a big thing. Like in a way, if you want to do that, okay, hey, I want my ATR to be robust and reliable. What should I do? So here is like we call 7 habits of ATR. Like some of the colleagues in my colleagues in Sensors Detector, they develop. So in order to develop a good ATR, we have to be like, how confident are you with your results? How sure and reliable are you? And understandable, how does it work? Do you know why you are getting the good results? So those has to be really, we have to learn. It's not that, okay, I give a data set and deep learning give me 95% accuracy. Oh, I'm so happy. But actually we need to know deep that, okay, why, how does it work? Then robust, is it gracefully degrade? Then out of library confusers, like how it works when if you have a out of library target. Then performance model, what is your performance? Then synthetic data, how does it work on all operating conditions with the synthetic data? Then sustainable end-to-end training process, how do you stay current if you get a new target? So the end, like you can see that like some people, they made their career on ATR. So if you really would like to do really robust ATR. So again, I'll not, the next couple of slides, I have more details, but I'll not go on that, but you can follow this paper to know more details on that. So again, like more details on the confidence of ATR, understandable, robust, and out of library distributions and ATR performance modeling. You can read more and more on those papers. So now back to the next 15 minutes that I have before 45. So I'll give you some example of results that we have done with a deep learning based SAR ATR. The first, this section, I'll show a single target classification with a civilian vehicle classification using CVDome data, and multiple target classification. What are the steps? So the associated paper with these two could be found on the paper listed here. So the civilian data set, so vehicle data dome. So it's like an X-band radar. Like again, you can use some tools, and this is how the ray tracing has been used to generate synthetic data. So now one thing comes out like, okay, when you have RF data set for training, so what is the impact of how do you start? So you collect the phase history data for radar. The first thing is like imaging. So imaging is important. So what type of imagery you used or technique used? So like within this SAR imaging, there is back projection, polar format, range Doppler, and phase history. So which one to use? So the real answer is that, okay, well, to save time, maybe polar format is good enough, because back projection imagery is actually n-cube complexity and takes more time. So we need to have some good results that gives us, good performance with the deep neural network model. So what the conclusion here is that we found that if you use polar format or range Doppler, you can get away most of the important features you need from SAR imagery. So however, back projection is very expensive. We may not need that imaging to apply. So that's the summary of this slide. So again, like here we show that how the target may look like in back projection imagery, depending on which azimuth angle and elevation angle you use. And then here are more information of how the SAR imagery look like. So the real thing is that that the SAR image formation is important, and so there is a trade-off. Like you may lose 1 or 2% accuracy based on what type of imagery you used, but polar format is the one that you can start and always start with. Then also like within deep neural network architecture, which ones are good? So like we found that among different models like ResNet 18 and MobileNet version 2, then ShuffleNet, AlexNet, and AlexNet Slim, you can make your own. However, you should always start with ResNet 18, because residual network 18. So that's like one of the model that you should always use. So overall, like the conclusion of the civilian vehicle dataset is that like what type of imaging we should use for RF applications or making RF imagery. So I think we should use the polar format, and also you may get good results with the range Doppler too. And also within this the deep neural network model, I think ResNet 18 is a good one to provide. And then another thing is training of the elevation angles is important. So like say if you train on like a 30, 40, and 60, and if you test on the middle like 50 degrees, that will be really good one. And another way of saying that if you train if your test data set is not covering the trained data, you may get really bad results. And also like in scenario 1, we try to show that, okay, well, let's take all different elevation angles that we collected and mix them up as a random, and for training and random for testing. That also gives you a good accuracy. But like as I said, like sometimes you may operate into a testing on a different elevation, but training on a some angle. However, you have to be careful in a way that, like say in this case, like if your testing data does not cover the train, you may not get good results at all. So then another thing you have to do is like confusion matrix analysis. So again, like when people apply deep learning for target classification, sometimes they don't do thorough analysis. So the confusion matrix must be done, and then it will give you like slice and dice as effect as much as possible how to exploit and to know all the details. So the confusion matrix analysis is important. So I'm not going to go details, but like these are self-explanatory on the slides. You can see on all the results here. So, but the analysis or using confusion matrix is a single most important thing to incorporate deep learning for radio frequency target classification. So now I think perhaps this is one of the most important sections, like for multiple target classification. So the previous section, civilian vehicle classification, these are like the single target and a single image chip. So, but in real world, we actually do target detection from a scene that has multiple targets. So how we do it? So the general framework is like we have a SAR image here, and we do the detector. So the detector, and then we do indexing based on the detections. Okay, what are the targets we detected, and then where the location in the imagery. Then we do the classifying of those image chip, and then and declare whether it's what type of target and where did we find. So the first thing of detection, like as you can see, like SAR imagery here, you can see so many targets here, then trees, and then other things on the imagery. So again, you can say, okay, well, now detection, what should I do? So in this example, we try to do with something called CFAR detector. However, before doing CFAR, we'd like to do that. Okay, well, this imagery, like SAR imagery, has lots of speckle and things like that. So you have to reduce like false alarm. You may do some pre-processing. So I'll not go details, but here in this case, we apply like a 2D wavelet transform to clean up those imagery. So what we found that if you do pre-processing, like say L1 minimization, or if you do any other compressive sensing technique, it actually cut off lots of the noise that may interfere with your detection and classification. So the real summary here is that apply some pre-processing on the SAR imagery for multiple target classification. That will actually cut some of those unwanted target. And then and also it reduces the detection, and so therefore when I have less detection and put to the classifier, it will give you good results for classification and less false alarm. So again, like I'll not go all the details. So like as I mentioned, like I give you like a snapshot of how this multiple target classification should be done. So here in this slide, like I'm showing like the circle, like how you analyze, like the greens are like that the target has been detected, and also you classify them accurately, that these are the targets and classification. And then sometimes you can have some red like a target that some clutter it may say as a target. So yeah, you can analyze the things. So again, like a real takeaway from multiple target classification is that you need to do some pre-processing to reduce the clutter, and then apply a CFAR based detector, or nowadays there is like other technique called RCNN or faster RCNN technique can be used with a CNN for multiple target classification. So again, like all of those details can be found in the book we have for your reference. So then now like I have about 4 to 5 minutes. I'll talk about the advanced research on SAR ATR. So possibly you'll hear that adversarial machine learning is a big thing everywhere. So like how to basically the goal becomes how to tackle the noise, whether it's adversarial or unintentional, and get the accurate classification. So I'll show some example here, how the adversarial imagery causing the problem. So like in this experiment we use like both MSTAR and civilian vehicle dataset to study. So yeah, here in these slides, we kind of try to take the RF signal or the phase history data, and we try to insert like a noise, different types of noise, and try to see, how those look like. So we saw that like this imagery really looks really bad, depending on how much like a noise you insert. So like here adversarial method, what happened so normally like the imagery is like an X, like the pixels. So what we do, X plus delta, you can put some some delta amount of noise, and as you increase those delta amount of noise, and it's actually performance degrade. So what we found that when you have adversarial imagery or noisy image, you have to do adversarial training to take the impact of those noise. So in general, like a classifier, like you have a two distinct boundary for two types of classes. But however, in adversarial training, it tries to fit into like here, like making the line. There's some wiggle room has to be there, so that you can really make a distinct between two classes of targets. You just cannot make a straight line for class A or class B. So that's in general what adversarial training does. So what we found that, like as we mentioned, that if we use like what type of robust deep neural network model to use, so we found that if you use like the ResNet 18 actually gives you good results because like it is more robust. And like here we have seen that like as we increase the like 0, 4, 8, 12, 16, and so on. So as we increase these are the amount of the noise. As you add more noise, the performance degrades. So that's kind of like a single most takeaway from this chart. But if you put the adversarial training, it actually kind of help you. So again, here is also we found that if you add more noise, then performance accuracy degrade. And here, like the solid lines and dotted lines are that solid lines use single polarization. However, the dotted lines are multiple polarization. So multiple polarization really give you better accuracy. And also like what we found, like the top dotted, like the line on to the top, this is like with ResNet 18, that gives you really really good results. So like a couple of things, resonate 18, then multiple polarization gives you really better accuracy on adversarial target classification. So because of the time, I may not go all the details, but again, like we have a paper on that, and you may read more details on that. So again, like we try to do with the phase error impact. So like you can see that we use like the different types of quad phases and how the impact. So again, like the real summary is that if you use multiple polarization and use resonate 18, and those things will help you for classification accuracy. Like if you have radio frequency interference, again, the multiple polarization and resonate 18 model, they'll give you better results than anything else. So the summary is like, small and fast models are not good for adversarial training. Resonate 18 is the best here, and also multiple polarization really also helps. So the future challenges with the SAR ATR, so like the transfer learning or domain adaptation are the area, then out of distribution detection, the real-time training, then sufficient statistics for object classification. Then there is an on-chip or online power-efficient learning hardware, then multiple target intelligence or fusion for target recognition, and then quantum machine learning is also coming in, and also the SAR ATR complexity analysis. So those are like in a summary, what it is. So like in conclusion, I think we reviewed the radar ATR and discussed deep neural network-based ATR implementation, and we also presented like the DNN-based recent ATR performance, and we just provided future research. So like before I go to the questions, and like some of the things people may ask, how do we trust the results and how the classification is accomplished by deep neural network is it true or not? Is this a black box? What's the validity of these results? So as you can see, like we are going to that area. So the deep neural network is not giving us like a so-called closed form solution, the exact answer. So however, we are trying to do different programs like a DARPA XAI, like explainable AI, and competency or machine learning. They are trying to do that, those kinds of area. So what about the ethics of applying machine learning for military operations? So like as you can see, people don't know the big picture of ATR. So ATR is huge. Like, so if we incorporate all the 7 habits of ATR, we know that we are not doing anything bad applying deep learning to the military applications. So having said that, I really thank you, and thank to CSIAC and the team here, Steve and all the people, and Mr. Joe Caroli for organizing this event. And I hope I was able to share with you the state of the art radio frequency target classification. And with that, I think I'm 3 minutes over. Thank you, Steve. And back to Steve.
Thank you, Tom. Yeah, a lot of interesting research you're working on there. So we do have a few questions in from the audience, and if anybody has any others they'd like to ask Tom while we have him available, you can just insert them via the chat function, and we'll run them by him. So one of the attendees noted that one of the most important aspects of SAR imagery is used to perform coherent change detection, CCD, particularly for military applications in all weather. So CCD usually, uses an algorithm. And so how might your research support or enhance this CDC analysis capability?
First of all, I think we have not done like the coherent change detection. So again, like we know that like the change detection involve like it could be coherent or non-coherent. So the coherent change detection like again involves like we have both a magnitude and phase, and they have to be really perfectly aligned, or like there is a approach called DPCA, displaced phase center antenna. So the first and foremost, like we don't have those data set as far as I know in public domain. So I have not started working on that. So having said that, I think again these are like the emerging area of research. So like as I say, one of the problem with the RF and deep neural network based applications is like we don't have data set. So I mean, like if there will be some data set, available, I think we can explore. But like we have not explored that because we don't have those data set.
Okay, thank you, Tom. Yeah, I think especially a lot of the work in with machine learning is the data sets are a critical key aspect in that processing. So let's see, we had a couple of questions. I think it was back around slide 27, 28 when you were talking about the ATR. Mm-hmm. And so one of the folks was wondering, what is the typical ATR processing times and latency times for accurately recognizing the object? And they were wondering, what is the probability of accurate?
Probability of accuracy, some of the things I think I cannot say to this venue, but like as you can see, with this public release data set, the accuracies are really good. Again, like good means like, okay, up to 90% accuracy. So if you think that, these data sets are sort of toys data set and we did good, so now how much time it takes, like say making an action. Let's say if you are the person who will prosecute like based on what you find. So these things could be near real time, nowadays. This could be near real time from sensing to the making the automated process. So I'll say, some delay, some seconds of delay. Second, it depends on the application. So one thing to mention, like when you make a critical decision, like, for time critical decision. So those are like, are studied very thoroughly versus like, say you are collecting like some data set, terabytes or petabytes of data set, but you would like to extract most meaningful information. So those are two different tasks. But like if it is a small area and you have been studied thoroughly that, okay, what are the things you're looking for, this could be done really in near real time.
Okay, thank you, Tom. And so another question was, how does your classifier perform with a group of targets in forming clusters?
We mostly tried, like say, instead of like the group of targets, we actually try to do of individual target recognition. So in other words, like we consider like say a group of targets. Let's say if they are if they are similar, then this could be done easily. But if they are completely if they are like a dissimilar, that will be like you need it could be done easily because they have a distinct feature. But if they are similar target and you make them group, I think this could be done easily. But we have not done those type of problem. We try to do like more of accuracy, like say, okay, hey, yeah, I have a T72 tank. We try to make sure that, okay, something is not T72 and T62 not to be confused. So we try to do more of like a single target, but they could be only 5 to 10% difference. So what can we do those type of situations than group of targets? So again, like I think within the community, research interest kind of varies, but I think we are trying to do more of a hard problem in a sense that we try to be two things. So we don't want to be false alarm, and we don't want to be that it is X or it is Y. We want to be more accurate on that versus like, okay, group. So, but I again, with our research, we did not cover like, the group.
Okay, thank you, Tom.
And again, like I think it goes back to the problem of like that. Okay, do you have data set? And so, like as you can see, the data is critical, and in RF domain, we don't have those type of data a lot.
So we had another individual. They were wondering if you had a recommendation for better understanding confusion matrices?
So like in general, like let's put that way. So like if I try to answer like first, like how people think of deep learning to apply for radio frequency target classification, people just say that, okay, wow, I applied my deep neural network to this target and I got 95% accuracy. But here we are trying to say that, okay, no, you have not done much. You need to do an analysis using the confusion matrices and show that how within target variability, how your deep neural network performed, or use as variety, or like say within changing the radar frequency or azimuth elevation angle, and all of those small thing that could be controlled, and then show me how these your results vary. So people are doing that thoroughly. Maybe those who does within the lab, these are not publishable. So like to answer the question of how we can interpret like the confusion matrix, again, it depends on how do you interpret. Let's say like if I have a 10 class, or if I have 10 class and 10 is a known class, then yeah, like it's easy that okay, you at least have a think that okay, you 10 class known and you trained, and it should give you the as accurate results, like show that okay, it's almost every time the confusion matrix shows that okay, it's almost good all the time. Then if you have 10 targets but one you just kind of holding class, or two of them you can hold class that you do not train, and then you're testing with this whole class, and then you can see that okay, well, either it kind of by mistake it's just untrained target call is one of the trained class. So those are like the way how the confusion matrix helps you. Like say, even let's say you have 10 targets that you are playing with, but like why don't you play, train with only 7 class or 6 class, and then bring 4 classes for the testing process and see that whether your classifier call 4 classes as out of library class, or it say that okay, the 4 classes as in library class. So that needs to be done. This could be revealed within a confusion matrix analysis.
Okay, thanks, Tom. So we got kind of a comment, I think it goes back to the group and the cluster. So the individual is proposing an example where our tanks are interspersed with enemy tanks at nighttime, and how do you distinguish the blue forces from the red? And so our tank commander suggests turning our lights on. So you just notes it's a group analysis, but it takes some form of human input, needed for the response.
Yeah, so like again, like there are some technique, like you can have some features, like make sure that like if you like to have someone like, hey, how can I recognize my guys from others? So therefore we have to make sure that with some of the salient feature that our guy has, we can always consider that one the prominent feature. So that will give us the latitude that okay, well, we know this is my guy. And maybe in addition to do that, like we may have some watermark, like say, hey, in addition to that, my guy has another extra features that that will say that okay, this is my guy versus the other guy.
And so another question came in. So does your tracker algorithm use the friendly tank ID mode to separate friendlies from the enemies? In order to focus on.
Well, we try not to be like explicitly spell out that okay, this is our guy or friendly or adverse guy. So we are just thinking that in general, like say. So the analysis we provided here, like, let's say if I have a civilian vehicle data dome, so like I can imitate that, okay, well, that the Camry, I can modify it or I can make the phase history in a way that, okay, I'll consider this is like has been changed intentionally, or it could be an enemy guy. So like we not try to put a label that okay, this is an enemy or things, but we just try to play within ourselves that okay, hey, this could be the things have been modified And now if I'd like to classify, how does the classifier makes a mistake? That sort of analysis. So I think it covered as an enemy or friendly. It could be said that way, but we did not say it explicitly.
Okay. Thanks for answering that, Tom. And I think with that question, we basically come to the end of our hour today. And I want to thank Tom for taking the time to share his expertise with us in this field. And thank you for the work you're doing, Tom. We appreciate it very much.
Yeah, thank you so much again, and thanks to the organizer, particularly Steve and your team, and also CSIAC and everybody involving and organizing this event. Yeah, so thank you so much. Actually, like one more thing, we have a more advanced topic discussion meeting. It will be at on April 27, hosted by IEEE. So yeah, if those interested, I'm just making an announcement. April 27, there will be a talk by IEEE, the distinguished lecture. So yeah, we have more advanced topic discussion. Thank you.
Okay, thank you, Tom, and thanks everybody for attending and joining us today. And we look forward to seeing you next month. I think we're looking at the last week in April. We're still trying to pin down a date, but we're going to have folks from the Modeling and Simulation Enterprise. They'll be giving a talk for our M&S community next week. So if you're interested in that area, we'll be sending out an announcement, and we hope you can join us. Have a good one, everybody. Thanks now. Bye-bye.